So the first thing we're going to talk about is integrating over some scalar function. So in general, you're given like a function, a scalar function, and the line integral of that function over some curve is defined as integral f ds. And so specifically in general, you can say that, say your curve is defined parameterization of your curve is like r of t. Your ds, so your differential, is going to be the arc length, or not the arc length, the magnitude of the derivative of your parameterization, dt. And so when you do the integral of f ds, you're going to do the integral with your parameterization plugged into your function times the magnitude of your derivative of the parameterization dt. And so here I give like concrete cases, like for n equals 2. If you parameterize your curve with like x of t and y of t, then we follow this formula exactly. And the same thing for the n equals 3 case.
That's a scalar, right?
Yes, over scalar function. Yeah.
What makes it this? What makes it this function scalar function?
So like if they write it like f of like a function equals something else, then that's like a scalar function. We'll see the second part. So this week is divided into 2 parts: integrals over scalar functions or integrals over vector fields. And so with vector fields, you'll see they always write it as like something dx plus something dy, or they might write it as like something I bar plus something j bar. The vector version for the scalar field, it's just a normal function. Okay, so a little bit intuition about what even are path integrals doing. So if you have some function f of x, and we have some path in the plane. So I'm going to draw a path. This is my blue path. I'm going to call it gamma of t. And it starts at t equals a, and it ends at t equals b, right? And so what is dl? dl is defined as our arc length element. So this line is dl, our arc length element, if we were to measure it. And what is a path integral doing? It's saying that if you have this function up top here, the integral of f dl is going to be the area of this curly red wall right here. And so that's the intuition behind a path integral. So what you're doing is to do the integral of this blue path of some function dl, we see that we start at t equals a and we go to t equals b, a to b. Our function, we're plugging in this parameterization because now we're kind of like seeing what it looks like on this path. Dot multiplied by the magnitude of the derivative of our parameterization, dt. So this path integral is the area of our curly wall right now. Any questions about that? Okay, so why don't we do an example? So it says like compute the integral of this, so path integral, where f is this function and c is your line segment. Whenever you're parameterizing something and they give you 2 points, no matter what, you can always use this definition. So you do 1 point plus t times, like this is kind of like your slope. So like 1 vector or 1 point minus the other point. So what do I mean by that? So I mean, you have, let's choose this. Well, I said that's P naught. This is P1. So we have 0, 0, 0 plus t times, we always do this endpoint minus the beginning point. So we have 1, 1, 1 minus 0, 0, 0. Or that gives us 0, 0 plus t times 1, 1, 1 or t, t, t.
So we can always use that definition.
Yes, if you have 2 points, no matter what, you can always use this definition to parameterize something. So common parameterization things are like, if you were trying to parameterize this purple line here, well, we know that no matter what, x could be anything, so we can call that t. But on this line, y is always 0. So this parameterization would be t0, where t goes from 0 to wherever this endpoint is. Like say the endpoint is a, goes from t to a. If you have 2 points and you're trying to parameterize the line between them, use this green one. And then if you have a circle to parameterize it, we know we always do like cosine sine. Okay, so now that we've parameterized it, we can just follow the formula. So formula says we do this integral of our function with the parameterization plugged in. So our parameterization right now is t. We plug that into our function. So now instead of x's, we see a t. So t minus 3t squared plus t. So it's going to be, what is our function? So t minus 3t squared plus t times the magnitude of our derivative of the parameterization. So that magnitude of 1 dt. Or that's t minus 3t squared, 2t. So 2t minus 3t squared. This length is square root 3 dt. And we could further keep simplifying. So you take the integral as normal, and then in the end, you would actually get 0. Any questions on this example? Yeah.
Just go up a little bit.
For most line segments, can you always force it to be between t equals 0 and t equals 1?
Yeah, you have to be clever about it, and you should be able to make it t from 0 to 1. Or if not, it would just be like t from 0 to 2. If your t is not from 0 to 1, the only thing that changes is your bounds here. It would be like 0 to whatever number you chose. Okay, so let's do an important property. So this is called additivity of your path integrals, meaning that if you have this one big curve and you can divide it into multiple parts, then we can take the path integral of the first over the first curve plus the path integral over the second curve, etc., so that we don't have to do one big complicated curve. And so let's do a nice example here. So here I have an example. Okay, so why don't you guys take 2 or 3 minutes to think about this example, and I will draw the picture on the board. Think about like what parameterizations you want to choose for each part. So like to start off, we have this huge curve, but we don't know how to parameterize this whole thing, but instead we can break it into separate parts and first parameterize C1, then parameterize C2, then parameterize C3. Okay, so let me draw what this curve looks like on here. Oops. So the idea, as I said, is that this whole integral is going to end up being the integral over the first path, C1, plus integral over C2, plus integral over C3. So let's do the first integral. What should I choose for my parameterization? Anyone have suggestions? How should I parameterize this line? Y equals -1. This is like -2 here, and this is 1. So you're just looking at, yeah. You have a question?
Would be like t and 0 or like t and negative.
T and -1. Yeah, because your x component t can be anything here, specifically between -2 and 0. So we can specify like t is going to be between -2 and 0. But no matter what on this line, y has to be -1, no matter what. So you can't do anything with that -1. So this is our parameterization for the green line. When we do the integral, so we're going to do the integral of C1 x dl. That's going to be the integral from t equals -2 to 0. This x, think of this as our function. We want to plug in our parameterization into our integrand. So what is x here? It's t. So I'm going to replace x with t. And we have to dot with, well, what is dl? That's the derivative of our parameterization, dt. So we need to find what is our derivative. So we take the derivative of the green thing, that's 1, 0. And so the length of that so this should be length. The length of that is going to be 1 prime equals 1. Because it's just square root of 1 squared plus 0 or 1. So in total, we have t equals -2 to 0 of t times 1 dt, or t squared over 2 for -2 to 0. Or we have 0 minus 2, which is -2. So the path integral of our function over this specific path is -2. That's the first part.
And how did you get the parameter, like the parameters for that?
This.
Yeah.
So we want to parameterize this yellow line here. No matter what, y is always going to be -1. Like you can't change -y. So I kept -1 here. But on this line, x could be 0, x could be -1, x could be -2. So it's changing. So I'm going to call that t. And so if we pick t from -2 to 0 because our line, if we plugged in -2, -1, we get like this point. If we plug in -1 for t, we get this point. If we plug in 0, we get this point. So this parameterization represents our line. Okay, let's try C2. What should I use for my parameterization for this? C2. This example is nice because they already gave you a formula. So what's a trick that we could use? Yep. So t and t cubed minus 1. Nice. Because instead of, we're choosing t as our x, and now if you plug in x, or if you plug in t for x, this becomes t cubed minus 1, which is y. So that's how I get the second thing. So this is my parameterization, and then we follow the same steps. Let's find the derivative. So that's going to be 1, 3t squared. And then the length of that is going to be square root of 1 plus 9t to the 4th. So our integral becomes t from, oh, I should have mentioned t here. It's going to be from 0 to 1 because that's what our x is limited by, right? So in our parameterization, t goes from 0 to 1. So for our integral, we have t from 0 to 1 of, what is x? X is t. Our length is the square root 1 plus 9t to the 4th dt. And above, in a hint, they already gave it to you. It's 0.94, so that we don't have to calculate this integral. And for our final parameterization, here there's another trick. So we're doing the integral of x over the third line, over the third path. But what happens when we plug in this path right now? Oh, it's kind of crooked, but this is supposed to be x equals 1. So if x equals 1 no matter what, when we plug in our parameterization, like some parameterization into our integrand, this x is 1. So we end up with just the integral over some path of 1 dl. So instead of doing any complicated integral, we can just find what is this length. That length is up here and at 2 in the picture. And so this length is just 2. Or if you wanted to actually try it out and do the integral, we can still parameterize it. So we would parameterize it as like the third path is going to be the third path is going to be 1t, and this derivative is 0, 1. The length of it is still 1, and so you end up with the integral from t equals 0 to 2 of 1 times 1 dt, or the integral of 2 dt, which will still give you 2. Wait, sorry. This is 1. 1, so this is t from 0 to 2, or 2. And so our final answer for this whole integral, remember we were trying to find this whole integral, so we add up our first part, for which we got -2. The second part, we got 0.94. And the third part, we got 2 again. So the integral of x over this entire path is 0.94. Any questions on that? Yes.
Even though we're integrating x, we can make the third line segment or the estimate t or whatever.
Yes. So like if we were trying to parameterize it, x has to be 1 no matter what, because our line is x equals 1. But y can be anything from 0 to 2. So this is the parameterization for it. Okay. So then let's see. Okay. Any questions before I move on to vector fields? Okay, so this is the second part of this week. Yeah. So we chose a parameterization 1t because no matter what, x has to be 1, but y could be anything. So it's kind of, this parameterization is like the opposite of what we did. Well, wait. This line is kind of like crooked. This should be a straight line. So like for this parameterization, we chose the -1 because x could be anything. One is y is always -1. For this one, we choose 1t because x has to be 1, but y can be anything. Any other questions about this problem? second chapter of this week the second part is one forms. So these are line integrals over vector fields. And so if you learn multi-calc before, maybe a lot of the language in like old textbooks is always using vector calculus, like vector notation. But now with Bryce's videos, he introduces this thing called one forms. This is a new language or like a different language, which is sometimes easier to compute like certain questions. So the purpose of one forms is that it makes things easier to compute. Okay, so first off, let's just sketch what a vector field even looks like. If we're given this vector field, so capital F is defined as Cx, Cy, meaning this is like your I hat, this is like your J hat. Or this could be like your dx term, or this could be your dy term. So a vector field can be given multiple ways. And so how do we sketch it? Well, let's say for now, let's choose like c equals 1, just so that we can graph this nicely. So our function is xy. This means if you are at a point 1, 1, or 1, 2, yeah, if you're at a point 1, 1, 1, 1, then f of that gives you 1, 1. So you have a vector in increasing one direction, increasing 1 to the right, increasing 1 up. If you had some point here that is 0, 1, then you have a vector going 0 to the right, but 1 up. That's this vector. And over here, f of -1, +1, you have a vector going left 1, up 1. That would be this one. And you can keep drawing all of these vectors, and you'll see that, let me do one more example, like 2, 1, 2. F of 1, 2 is 1, 2. So at 1, 2, you have a vector going 1 to the right, but up 2. So this line is longer. So as you get farther away, the lines get longer. And so this represents a uniform expansion because you're uniformly expanding outwards. Yes.
So if they're both have seen for how can we put 0, 1?
So right now we're saying like C is 1. But if C is 2, then all of these would just be multiplied by 2. And it would be the same pattern showing up.
How did you get like
F of 0, 1. So by your definition, f of xy is xy. So 0, 1 is just 0, 1. So at 0, 1.
How did you choose number 0? Like, why did you?
Oh, I'm just testing points to see at certain points what does the vector look like.
Okay.
So that I can see overall what is like the pattern.
Okay, I get what you're saying.
Yeah. Yeah.
But then with that, isn't the value? Oh wait, C is okay.
Yeah, C is 1. So I just as like a test. If C was any other number, you would still get the same pattern of outward expansion. Just these lines would be, this line would be like longer, and then this line would be even longer.
And if C was negative?
If C was negative, then it would be uniform collapse. Yes, collapsing.
How do you know like the direction of the vector?
So the first term, no matter what, is going to be in the x direction. If it's positive, go right. Negative, go left. The second one is always your y direction, no matter what. So positive, you go up. Negative, go down. Okay, so why don't you guys try this next one then? This function is, and you can test it again, like c equals 1, and see what happens. Okay, does anyone see any patterns? Okay, let me give you guys a first point. So like if I wanted to test the point 1, 1. So right now our function is defined as negative y x. So here y is 1, so it becomes negative 1. X is still 1. So at the point 1, 1, we have a vector going 1 to the left, 1 up. So left and up gives me this vector. What about negative 1, 1? Right now, y is 1. So negative of that gives me negative 1. X is just negative 1. So at the point negative 1, 1, our vector is going 1 down, 1 to the left, because negative, and 1 down. So it's like going this way. What if I tested one more, like 0, 1? That gives me y is 1. So negative of that is negative 1. X is 0. So at 0, 1, I have something going left 1, but 0 in the y direction. So it's just going straight this way. So now does anyone have any?
It's like a rotation.
Yeah. So it's a rotation in the clockwise, counterclockwise way. Counterclockwise way. So it's going like this way. And you can just keep testing points as I did to see the pattern. Okay. Any questions on drawing vector fields?
So we were assuming C equals 1, right?
Yeah, we're assuming C equals 1 just so we know how to draw it. But you could assume C equals 2 and try to draw it too, if you wanted to. But because C can be any number in general, it's going to have the same pattern. Okay. Any questions on that? Yes.
That's like the X and the Y like written like the other way around. It doesn't matter. Like
No, it's fine that Y is here and X is here. Yeah. That's what this vector field is defined as. So then let me give you guys some more intuition about what these integrals over vector fields look like. So it's very similar to path integrals, which we just did, but with a different perspective. Now we're looking at things in like one form way. So suppose you have this vector field, right? Capital F. Some one form field, as we saw above, I said the first component is like your I term, like your I hat. The second component is like your J hat component, your term. So any vector field is always written like this. You have something times I hat plus something times J hat. And say you have your differentials also. You need like your dx bars. Dx bar is like your first component, dx1. Second component is like dx2. So you have this f bar, dx bar. Then what is f bar dot dx bar? You're taking the I components and you multiply them, right? So you have f1 x hat and you have the dx1 hat as your I term. So I won't write the I, that's your first term. Then you dot product this, the j terms, right? Which gives you f2 x hat bar, dx2 bar. And it would keep going if you had like more terms like f3 or dx3. So what is, if you did the integral over some path of f dot dx bar, what are you doing? You're doing the integral of this thing. So happy. Okay, we're doing the integral of that. And so what does that mean? Let's draw it. We have some path, which I draw here in blue. And, oh, wait. Okay, and say we have as dx1, we have this point A over here in green. F bar, like this first component, let's say it's like some vector that looks like this. This is F bar. And dx bar, this always has to be tangent. We're saying that dx bar is going to be tangent to our path. So it's going to be this line here, dx bar. What if we had another point, this point B? Well, our dx bar has to be tangent again. So let me draw our tangent line. And say our vector, our function vector at that point looks like this, F bar. And say I had one final point like point C here, point C. Again, we have our tangent dx. And say at that point, we evaluate F bar and we see that it's this vector here. We see that it's perpendicular. So when we do the integral of this whole thing over some path, what are we really doing? We're doing the dot product of each F bar with the dx1 bar. So you're doing this dot product, this red one and this orange one. Plus, you're doing this dot product, this orange one, this red one. Plus, this dot product, this red one and this orange one. So the integral of f dot dx over this path, it adds up a bunch of dot products along your path. So it adds up a bunch of dot products along path. And what it turns out that this thing, this f dot x bar is what we call a one form. So now we have this new notation, this alpha f bar. This is called your one form. One form. And we define it just as we did above. The dot products of your f and your dx's. So when you do the integral, when you're integrating a one form, you're doing the integral over some path of this alpha. And what you're really doing is you have the alpha with your parameterization plugged in. That's how we're getting these orange lines, right? We have to plug in our point to our function. Then we multiply it by this derivative because that's like our tangent line. Those are like the red things, ln dt. So this is what it means to integrate a one form. Any questions?
Like, what's the significance of the dot product? Like, and why wouldn't it be a cross product?
It's a dot product because you have a vector and a vector. So, but in order to integrate it, we need a scalar. So we should dot product it because then it gives us a scalar. Yeah.
So when we're integrating the scalar vector, we use the length of the derivative, and then when we're integrating
Over a vector field.
vector field, we kind of convert dt to dx, like using that dx dt.
Mm-hmm. Yep. So yeah, if you notice, like earlier in the class, we multiplied by the magnitude of things. So if we're doing an integral of a scalar function over a path, we do the magnitude. But now we're doing an integral over a vector field. So here we have dot products instead. Yes.
Say that like one is times and one is like in terms of the vectors.
So dx, the dx's are tangent to our path.
Okay.
And f is these orange lines are if you have your function and you plug in a, your point. Then you get, we get this orange line. So that's kind of like how here we would plug in our parameterization into our function so that we can get all these orange lines.
Okay.
Yep.
So alpha like decomposing like the tangent vector and other vectors like the x, y, and d4 like as your J vector.
Yeah. Wait. Yeah. Yeah, this is like above here where I was like dot plotting like the I parts and then the J parts. Yep. And so why did I mention this? This relates to practice problem number 9. So question number 9 says, suppose C is a level field for some function. Explain why the integral of this one form is 0. So this question is saying, explain why this whole thing equals to 0. Well, knowing what you know about what does our one form look like? Our one form is the dot product of the orange and the red plus the dot product of the orange and red. We're dot producting them all. How could we get 0? That only happens if your dot product is 0, right? So if this product is dot product is 0, we have 0, plus this dot product is 0, plus this dot product is 0. Then when you add up a bunch of dot products along a path, you get 0. So that's why the answer to our practice problem question is this first choice. The dot product between your tangent vector to the level set, so that's like our dx, the red line, and the gradient, that's like our orange line, is always 0. Any questions about that? Yeah.
Does this have anything to do with the like part in the video where it's feeding a vector into
Yeah, so that is like, let me see, I know what you're talking about. So that's, he said the one form, you're feeding them like tangent vectors that give you scalar fields. So it's kind of like you have this F1 thing and you're feeding it this tangent vector, this dx1, which we said is the red one tangent. So we're like feeding this into our one form and adding them all up.
So this is a practice problem. So F is gradient. Like vector F is the gradient.
Yes. Yes. So like if these orange ones are now the gradient, well, the gradient dot product something else can only be 0 if the gradient is is orthogonal to the level set. So that was from like a few weeks ago where you have some level set, this is your gradient, they're orthogonal. And we're dot producting all of these. If we're dot producting them all, they can only be 0 if they're orthogonal. Any other questions on number 9? Okay, and this also relates to number 10. So it says, let's say we compute the flux across a level set. What can you say about our integral? So the integral above. Okay. Does anyone? Okay, okay, let me explain. So flux, so I didn't do the definition yet, but maybe you guys already saw that flux is going to be f dot dy negative dx. Like when we do flux, we do n negative m. You'll see later. So above in question 9, we were doing f dot dx dy. We kept everything in order. We were doing our function like f1, f2, dot with the x dx and dy. So like the I components, the j components. Flux switches them and then negates the second component. That's what flux is doing. So imagine if you have some point in our normal so we have dx dy, say dx dy is 1, 1. The black dot. Then dy negative dx, if I want to transform it, that would give me 1, negative 1. So 1 dot 1, oh, sorry. this black line. One goes right one and down, wait, one, negative one goes this way. Wait, one, negative one. Sorry, one, negative one is over here. So I have my 1, 1 dot, which goes one right, one up. At this point, 1, comma, negative 1 here, we have a vector going 1 to the right, 1 to the left. So what was this direction?
The black arrow, what does it represent? Just a normal.
This represents 1 in the I hat direction and 1 in the J hat direction.
Yeah, but like,
So it's a,
so it's just normal, right? Like vector field.
yeah, it's a normal vector. Yep, so if I go from the black vector to the purple vector, that is a 90-degree rotation clockwise. Okay, so now going back to our picture, we have some path. And originally in question 9, we had our gradient. So let me do it in orange. We had our gradient being orthogonal to our tangent vector. So let me draw my path this way. Gradient. This is our tangent vector. Yeah.
You just on the flux forward, it's a 90-degree change clockwise, but on that practice problem 6 that you talked about on counts or whatever, you said
Mhm.
you like showed how it was like 90 degrees counterclockwise, and that's the right answer. So why is this for 90 degrees clockwise?
Flux. Wait, flux 1 form.
Like from the oh wait, but that's from the work one from the flux one form. Did you just or wait, that's a work one form, right? When it's just like
Yeah. Okay, okay. So say it's 90 degrees. Okay. Say it's 90 degrees counterclockwise. Okay, it still works out. Anyway, so we have, this is our dx bar. In question 9, we had our gradient orthogonal to our tangent line, and we got that dot product is 0. But now, based on this transformation, this red transformation, we're saying that we're moving our dx bar 90 degrees counterclockwise. So if we move our bar 90 degrees counterclockwise, that's moving it this way, 90 degrees. So now this is our dx bar, right? I moved it from our dotted line, our tangent line, 90 degrees counterclockwise, because now we're considering the flux. So what does that mean? That means that our dx bar is now parallel to our gradient. So what should that imply?
It's 1, right?
Maybe, what can it not be?
0.
Yeah, it cannot be 0. So it is definitely not 0.
Like, so is it 90 degrees and counterclockwise, with flux, or?
Yeah, it should be counterclockwise. According to number 6, I believe.
So how would you do then, like the previous drawing when it was that way? Like you had a drawing that you like erased that was like.
So right now in purple, I had the tangent like this way. And clockwise is still this way. So it still give you this line, this red line. Or if you wanted to start at the purple and go counterclockwise, then you get the same line as the gradient. It's still parallel. Yeah, it's definitely not 0. So the point of this question is to realize that your dx bar is parallel to your gradient. So the dot product can't be 0. That was the point of this question.
like in flux, the dx bar is parallel to the gradient, but
Yeah.
in work, it's tangent.
Yes. So in Yes. So in question 9, it was tangent, so they were orthogonal, the dot product was 0. Now in flux, the dot product cannot be 0 because they're parallel. Okay. Any other questions on these two problems? Okay, because we now have a full recitation, let's take a 5-minute break so that we don't. Okay. So this example, and integrate it over the unit circle in a counterclockwise direction. Okay, so we have f. This is 3x plus y. df, the gradient 1 form, is going to be, you take this 3 and you write it as dx, right? Because according to our definition, we have like the partial, the partial with respect to x, dx. So here the partial with respect to x is 3, you have 3 dx. Then plus partial with respect to y is 1, so you have 1 dy. So this is our df, our gradient 1 form field. Then we need to integrate it. So how do we integrate it? We always need first to parameterize no matter what. Here you have a circle. So circle, you always want to think cosine sine. So we just parameterize it as cosine sine. We're going to need to take the derivative, which is negative sine cosine t, and follow our formula. Our formula for df over some path is df with our parameterization plugged in, dotted with the derivative. That's our definition. So now evaluating it, what is our t? T goes from 0 to 2 pi. What is our df? Our df is this, 3, 1. 3 is our first component, 1 is our second component. So 3, 1. And if we were to plug in our parameterization, well, there's no like t's here, so there's, or x's, so there's nothing to plug in. They're just constants. Dot with, what is our derivative? That's sine t cosine t. So we have the integral of negative 3 sine t plus cosine t dt.
What happens if it wasn't a unit circle?
If it wasn't a unit circle, then you would have some other number here, like whatever the radius is, like 2 or 2. And you can always check to make sure that you have the correct parameterization. Because say you had x squared plus y squared equals 4 is your circle. If we use this as our parameterization, that would give us 4 cosine t squared plus 4 sine squared t equals 4, which we know has to be correct. Oh, yeah. So df, here is our definition of df. We take the partial of the function they gave us with respect to x1 dot and then dx1. So let me copy this here so we can see. So our first variable is x. I take the partial of f in yellow with respect to x. That gives me 3. And I need dx. Second variable is y. Take the partial with respect to y. We get 1. And I need dy. And this is our, yeah.
Were we given the bounds of 0 to 5?
No, we had to solve, we had to come up with it. But we know it's 0, wait, 0 to pi or 0, sorry, 0 to 2 pi. Because it's the whole unit circle. Integrate it over the entire unit circle. So no matter what, we start at 0 to 2 pi. Yeah.
Like, you could also plug in like, wait.
So the dx or dy are similar to I and j.
Yes. Because we're in vector field notation now.
Just this gradient 1 form means 1 form in which or like because
One form.
you have can you scroll down?
Mhm.
Yeah, you have like df equals 3 dx plus 4 dy, and the original function was f is equal to 3x plus y.
Yeah. Oh, yeah. Yeah. You said the derivative of the one form is what?
Isn't that like a scalar function?
Yes. So we have to, so we first like compute the gradient one form of f. So we kind of made it a one form notation, which would have been like 3x y, or like 3xi bar plus yj bar. And then we take the gradient of this one form. The gradient of this one form is using this definition, or you could just do the partials and dx partial dy.
So the gradient one form is putting into like one form notation with the derivative.
For this gradient one form, the path that you take does matter, but it's different because I know the gradient one is also used for independence of path, but in this case, the curve does matter when calculating the one. But in independence of path, the gradient is used for something else.
Well, you'll see this question actually relates to the independence of path theorem. Yes, I'll get back to that. Yeah.
Can you scroll up? Like that.
Oh,
What's the answer?
we haven't finished.
Oh.
So we could continue integrating. And so you get like 3 cosine t plus sine t from 0 to 2 pi, or you get 3 minus 3, which is 0. And so this 0 is very interesting, the fact that we got 0. Why is it interesting? Well, we'll see in a bit. It relates to a certain theorem. Okay, any other questions on this problem? Yes.
It's always the case when you use gradient one form path, it'll be 0.
Not necessarily. It depends on the path. Oh, that's what you're saying, right? Yeah, it depends on the path. Wait,
In this case, the path does matter.
yes. Yeah. Oh, okay. Okay, let me go to the, yeah.
What does that mean? Like the fact that we got the 0. Like, what does that mean?
Oh,
Like, what does it mean?
so it ends up meaning that because we're integrating over this unit circle is considered a closed loop, meaning that the end point and the start point are the same. So when you're integrating it, I guess it means like everything cancels out when you're doing the dot product. Like when we were doing the integral of the one form above, we were doing all those dot products, right? We were doing all these dot products, and so it turns out like they're all the gradient itself, and so the dot products are 0. And also the path starts and ends at the same point. So like there's no, like the dot products all add up to give you 0. It's kind of,
Is that the case?
if it was a closed loop, yes. But if it was not closed, like some other loop, then you can't just say it's 0. It might be something else. Okay, so let me go to this theorem, which everyone is touching on. Oh, here I just have like a quick summary of the 2 types of integrals we learned this week. First one is scalar path integral, where we have like the magnitude. Second is what we've just been doing with the one form, and that's the definition. And 2 examples of the one form, which we'll learn, is the work and the flux, right? Okay.
Is circulation just another version of flux? Only another version. Flux.
Circulation should be, I think circulation is different from flux.
Yeah, it's the same thing as work. Right?
Let
It's
me,
written in the MDX plus N slide form, which is how it's written.
yes, I would say they're similar.
We said that circulation is in a
Yeah, in a specifically in a closed loop. That's why there's this circle thingy.
Only ask the circulation. when there's something in the circle.
Most likely. Okay. So let me, okay. Actually, before I get to the important theorem, let me just say the definitions of like work. So work is just you're doing a path integral again, the first version. So f, like integral of your one form or integral of f dot dx. Circulation is just a path integral. So yeah, it is just work, but over a closed loop specifically. So for work, you just have some random curve, whatever. If this curve is closed, or sorry, if it's just a loop, meaning that it ends and starts at the same place, then we call it circulation. Okay, and then the definition for flux, as we saw in that practice problem, is m dy minus n dx. For your function is always going to be written as like m n. So the components kind of switch and then you negate one of them. Don't forget the negative sign. Okay, and circulation, by the way, measures the tendency of your vector field to flow on the curve, or meaning flowing in the same direction. So there's a practice problem like 30 something, where if you have this vector field that goes this way in the black arrows, and your curve is the red one going this way, then you can say that the circulation of this is negative because your vector field is going one way, your curve is going the other way, right? So you're not flowing in the same direction, negative. Yes.
And usually for circulation, the answer is something like 2 pi r squared or whatever. What does like that mean in the context of
I don't think it's, I don't think it's always 2 pi over
usually?
Usually,
For example, like, you get the
usually it's like 2 pi because our path happens to be a circle. So we're always doing it from like 0 to 2 pi. So like a 2 pi always shows up. Because when we're doing this, the first step is to always parameterize our path. And when we parameterize it, we always do cosine t sine t, where t is from 0 to 2 pi. So then when you do integrals, there are probably like some cosine terms, some sine terms, and you're doing it from 0 to 2 pi. So like a 2 pi would show up when you're evaluating.
yeah. My question is, and for example, if you, 1 plus 1 is 2. If you're calculating the length, then you know that the length is 2. But in this case, if you get an answer, like, does it mean that it's circulating, and if it's positive, it's in the same direction, and it's 2 times the original? Right? Like, I don't really get
I don't think it has to do really with length. The circulation is telling you like, are you flowing in the same direction as your vector field? So if it's positive, that tells you, yes, you're flowing in the same direction as your vector field that you're integrating over. If it's negative, it means you're going in the opposite direction. Is like, it's not having to do really with like arc length or length. This path is just saying you're integrating over this specific path and you're traveling around along this path.
So with that example, we drew the vector field and then the top, that's negative circulation.
Because our vector field is going this way, counterclockwise, but our red path is going clockwise.
What's the equation for circulation? FDR.
Circulation is, this is like fx dx plus fy dy.
So FDR, right?
Yeah, it's the same as, you're still doing just a normal path integral, this integral of the one form.
Okay, so the only thing that changes is
Is the path that you're like parameterizing.
the flux. When you do flux, it goes the other way around.
Yes. Yep. So work and circulation are you're just doing the path integral itself. Okay, and then, but say this red path was traveling in the same direction. As I said, it would be, your circulation would now be positive. Okay, Any questions before I do the theorem? Okay, theorem. First, let's go over what conservative means. So F, some vector field, is conservative on some domain, some region, if your function is path independent. Meaning that whatever curve you choose, it doesn't matter as long as you have some like boundary point, like a start point, end point, your integral f dot dr will always be the same. So like no matter what path you take, or in the one form language, the integral of your one form equals is the same, regardless of the curve you choose. And so now we get to the independence of path theorem, which kind of uses like the fundamental theorem of calculus a little bit, but we can consider it as independence of path theorem, which says that if f is has some continuous derivative, so it's like some function, and you have a start point and an end point, boundary points, then the integral of your gradient dot dr is going to be f of your endpoint. So evaluate your endpoint to f minus you evaluate your starting point in f. With the one form language, it's written in the green. So you have integral of this gradient dot dx. What did we say gradient f dot dx is? That's the one form. Where notice here, this is the gradient in that subscript. What does that mean? Well, that's also written as df, we saw. And because we have an endpoint and a beginning point, by the independence of path theorem, says that this integral can be f of your endpoint minus f of your beginning point. And so the example we did before all this, where I said like somehow we got 0, that happened because our endpoint equaled our beginning point. So if we have some function and our endpoint equals the beginning point, that means f of b equals f of a. So when you do f of b minus f of a, you get 0. And that's why it happened to be 0. So instead of doing that whole integration we did above, we could have just noticed this pattern and said by this theorem, it's 0. Yes. This is alpha with a subscript gradient. This is triangle f. Right. Alpha gradient f.
So the independence of path theorem is always 0.
Not necessarily. This is only 0
Oh, okay,
because it starts and ends at the same point. But otherwise, if you had something like this curve, you can still use independence of path theorem. It would just be f at this point minus f at this point. Yes.
Finding is just like any like like work the flux or just an integral over the
yes, specifically where your function has to be a gradient.
okay, but it's used to find any integral of with the vector field anyway.
Yeah, so it's like f dx, but like it has to be your gradient. And this, you can only use this theorem if f is a gradient, which we will show if it's a gradient by using the component test. Okay?
For whenever we get like a gradient one form,
Mhm.
if we're not told to use the independent path theorem, we have to first that it is independent of path in order for you to use that theorem.
Yes.
And it's not that we just use the regular.
Yes. Yep. Mhm. Yeah, if it's some like difficult thing, like if you try doing the component test in something, yeah, you should check.
What happens if you're not given the gradient?
So you have to find it, and that's the next step. So we'll have to find. So if you're given, so according to our formula, if you're given this in the gradient form, on the right side we need the actual f. F here is called the potential function, and so we would have to find the potential function, and there's 2 methods for that. I don't know if they would tell you specifically to use it, but if something, maybe like the problem gets really complicated, like you're trying to do it the original way with integral f dot dr, and it's getting like really complicated, maybe it's a sign that there's some trick And the trick might be that you can use independence of path theorem, because using independence of path theorem makes the problem much easier.
But it's just like additivity, right? Or no?
Activity is like adding up path integrals. This is not. This is like finding your original f function and doing like the endpoint minus the beginning point.
Oh,
So could be the case for problems where they could give you a curve, they could give you a function, and you would have to determine whether or not that's independent of path, and then you discard the curve and just go straight to the independent of path.
Yes, exactly. Yeah, and it's especially a very like good sign if they gave you like Pavel said, they gave you some like path like gamma of x is defined by whatever, and they say like you have a boundary point like 1 0. Wait, no, and they say like starting at x equals something like a to x equals b. If you end up plugging in a here and you get some point like 1 0, and you plug in b and you also get 1 0, then that makes things much easier because it's probably a closed path. You can probably use independence of path theorem and it's going to give you 0 instead of like doing out all the work. So if you plug in your points, whatever point, and you find the starting point and the ending point are the same, most likely it's going to be independence of path theorem. Okay, so let me go over this component test. So in order to make sure that it is a conservative field, or meaning that your function is the gradient, or meaning in order to use our theorem, we have to use this component test. So the component test says that we check that all of these partials are equal for all I not equal to j. So what does that mean? So let me.
So the component test is to determine if the function is also the gradient. Right?
Yes. So do the component test first. If it's the gradient, then we can use the independence of path theorem. Then if you have a starting point and an ending point, you definitely can use independence of path theorem. So let me do this example. Okay, so let me get rid of this. Okay. So they give us a capital F. Capital F is defined like this. This is our like M, our X component, I hat, plus this J plus this K. We have to determine whether all these partials are equal for all I not equal to J. What does that mean? How many different components, how many different things do we have to test? If I is 1 and J is 2, that means that we have, so let me first write, this is our M, this is our N, this is our P. So I wrote M and P. What are our variables? X, Y, and Z. So I wrote X, Y, Z. So whenever I refer to something as like capital F1, sub 1, that would be referring to like M. Capital F sub 3, that would be referring to P. If I said X2, that would be referring to the Y term. So if I equals 1, J equals 2, that means we're doing the partial of F sub 1. That's our first component here, M. X sub J, X sub 2, that's our second variable, partial with respect to Y. Then F sub 2, that's N, that's here. X sub 1, that's our X. So I equals 1, J equals 2 gives us this equality that we have to check. Now you might say, what if we have like, why aren't we checking J equals 2, I equals 1? Like, do we need to check that? Well, what would it give us? This would give us partial of F with respect to, sorry, let me write it in the like, I equals 2, J equals 1. So this would give us partial of F sub 2, that's N, over the first variable. Is that equal to the partial of our first thing with respect to our second variable? This equality is the same as this equality. So we don't need to consider this. That's like double checking what we already did. So let's check if this is true. Partial of this yellow highlighted thing with respect to y, that will give us,
But what with respect to y and not with respect to z or x?
we will continue. So we have other things to check too. But let me first check this one. So this is the first thing we have to check. So partial of m with respect to y, that would give me negative e to the x sine y plus z. Partial of the green thing with respect to x, that would also give me negative e to the x sine y plus z. And so they are equal. What is the next thing we have to check? I equals 1, j equals 3. We also should check I equals 2, j equals 3. So there's 3 things we have to check. 1, 2, 3. So what would m with respect to z give us? So that's the partial of the green thing with respect to z, which gives us, well, there's only one z thing here, which is x. M with respect to z is the yellow with respect to z, just y. Partial of p, that's the purple one, with respect to x is y also. They are equal. And the same thing for the last one, you get x equals x. So all 3 conditions are met. We passed the component test, so it is a gradient. Yes.
If it's 2 variables, you just have to check that first.
2 variables.
If it's only in x, y.
Yes.
Like, are you given the I equals 1, j equals 2, so you know what to check, or you just randomly?
So we know we're only given this question in black.
Yeah.
And so we need to check by the component test. We should check this for all I not equal to j. How many things are there? How many terms are there? There's 3. So I could be 1, 2, or 3. J could be 1, 2, or 3. And so what are all the different combinations of i's and j's? It's this one, and this one. Yeah.
Would they ever give us like in terms of x and y? We have to assume that there's like a hidden z and check. I think it makes sense.
If there's 3 things like an ijk,
Yeah.
there should be 3 variables.
Okay, so
So like however many components you have, that's how many variables you have. And so that should go up to like I equals whatever number it is.
okay.
Do this so you can like see what's common between them to make a differential function.
Yeah.
And if there is one, then it is conservative.
Just by checking that these 3 conditions are met, we know that it's conservative already. And then in order to use the theorem, like in order to use the independence of path theorem, we need f of, I scrolled too far. We need f of b, like the original f function. So we'll need to find the potential function. So let me find the potential function real quick. So we just checked that it's conservative. Now we need to find a potential function. First method is to kind of like guess and check. So when we did the component test, we already found these partials. We found the partial of f with respect to x, with respect to y, with respect to z. Now we need to find an actual f so that if we took the partials, we actually get these 3 things. What does that mean? This first partial, let's take the integral with respect to x. So we're going backwards. If we take the integral with respect to x, we get e to the x cosine y plus the integral of yz with respect to x, that's xyz, plus some other term with y's and z's in it. Because when we have this function and we take the derivative with respect to x, there's no x's here, so it becomes 0. So in fact, it is true that the partial of our right side will give us the left, but we don't know what this red thing is yet. Then the second one, let's take the integral with respect to y. So we get xyz plus e to the x, let me write it in orange, e to the x cosine y, again, plus something in terms of x and z's, so that when we take the derivative, it doesn't show up here. And same with the last thing. So we have integral with respect to z, x, y, z, plus half z squared, plus something with x's and y's in it. And so we know that no matter what, let's look at the patterns. No matter what, this x, y, z always shows up no matter what. So we know x, y, z has to be in our potential function, our original function. That way, when we take the partials, we see it show up. We also see these, the e to the x cosine y. That means this orange one should be e to the x cosine y. Sorry, that's a bit hard to see, so I won't highlight it. So we have this e to the x cosine y. And then lastly, we need this half z squared to show up. Because when we take the partial, we need it to show up in this partial. And when we have half z squared over here, if we took the partial with respect to y, it would disappear anyway, so that's fine. So our final potential function is this. And you know, when you take integrals, we always add the plus c thing. So you could add a plus c there for some constant c. And so this is your potential function. And if they gave you a start and end point, you would use this to put an end minus start.
So for that first line,
Uh-huh.
you're putting return characters in X, Y, Z. And it's for C, it's like with respect to Y.
Yeah, if you take the partial of like this c of y, z, this means some function with y's and z's in it. So it could be like y squared plus z squared, whatever. But there's x, yeah, yep. Okay, all right, recitation is over. So let me end the recording.